Hello, I'm James and welcome to Synthetic Faction. Today's project is this robot arm. This is going to be part one of a series in which I'm going to be building a full-scale humanoid robot. Today I'll show you how I built this thing and what the problems were that I faced. This robot arm is going to be a version 1. I do plan on making a version 2, possibly 3, and I'll be trying out other types of actuations within these prototypes. I'll be doing this to see what works best and what the pros and cons of each of them are. This arm is fully 3D printed, so anyone with a 3D printer can build their own and just buy the other components they need online. Also, I'll provide all the CAD and the code in the video description. So without further ado, let's get cracking. So when I set out to do this project, I was trying to make it have as much movement and dexterity as the human hand does, and at the same time providing the robot with a decent amount of grip strength. This proved to be quite the challenge, getting all of the mechanical movements of the servos to create actuations that replicate the human hand. When I started designing this arm, I modelled it around my own arm, while trying to maintain the same dimensions of my arm, which was handy because I got fairly big arms. This kind of made it easier, as one of the most challenging things about this project was fitting everything into such a small space. The problem was, because there were so many joints to actuate, it was difficult to actuate them without hindering the other joints. When it came to creating the motion for the arm, I tried to replicate as many movements as I could while trying to maintain an organic, lifelike motion, but eventually found the limitations of this design and ended up settling on something that was the most essential and most used motions within the hand and arm. The way in which I performed all these actuations within the hand and arm was by using a total of 10 motors to perform all of the actuation for all the joints. These motors were 4 SG90 metal geared servo motors, 5 JX 14 kg servos, 1 large NEMA 17 stepper motor, and also a CNC stepper motor driver to control the stepper motor positioning. So let's take a look at the overall construction of this to see how it all works. So when I set out to design this robot arm, I wanted to have as much movement as the human hand and arm did, but at the same time being able to fit all the components into a compact space that is the same dimensions as the human arm. The motions that I was able to achieve were the overall inward finger motions so that the hand can open and close, and the side-to-side motions of the fingers so that they can dynamically grip objects. The thumb, unfortunately, is only able to move inwards and is not capable of side-to-side motion. I did previously attempt this in a previous prototype, but unfortunately it didn't work for me. For one, I had no more space to fit the Kevlar fishing wire through the base of the hand, so I ended up having to use these ugly PTFE tubes sticking out the side of the thumb joint, which I really didn't like because they ruined the look of the robot arm. I could have probably suffered it if the joint worked well, but unfortunately it didn't even work. The problem was the pair of Kevlar lines that actuated the thumb joint would just end up hindering each other. Whenever the servo that controlled the side-to-side motion of the thumb moved the thumb side to side, it would jam up the main Kevlar line that moved the thumb inwards. There really wasn't any other way for me to actuate the thumb side to side without increasing the size and making the thumb look stupid. The problem was it was just not possible with this type of design, in which the servos are in the arm area actuating the finger joints, especially when you're trying to keep the arm the same size as a human arm. It may have been possible if I made the arm ugly and big, but that was not the look I was going after. Another joint that I was not able to achieve with this design was the forwards, backwards and side-to-side motion of the wrist. I did attempt this in a previous prototype, although I admit it was an afterthought and I didn't have it in my design initially. The problem was also another space issue. There was physically no more space in the arm to mount any more servos discreetly. I ended up finding some space in the wrist area, but yet again ended up with this weird looking crank thing to help actuate the wrist forwards and backwards. I also didn't like the look of this, as it looked ugly and was not in keeping with the natural look of the human arm. Another issue is, it didn't work. The problem was I could only fit smaller servos due to the space limitation, so it wasn't the most powerful to begin with. The lack of power played a part, but the main issue was the PTFE tubes that fed the strings to actuate the main motions of the fingers. These tubes turned out to be too stiff for the small servo that just didn't have enough power to bend all the PTFE tubes, so at first I tried cutting a little section out of the tubes to make them a little bit more flexible, but this was still not enough for the motor to actuate it properly. I then decided to cut them off completely out of the wrist area so that the servo was able to actuate the hand. This totally messed up everything. I may have been able to do this joint if I was able to tension the Kevlar lines, as the problem was when I moved the wrist back and forth, the lines connected to the finger would lose tension, and without any way to constantly keep them tensioned, it would prevent all the fingers from working correctly. It could have been possible to tension the cables, but yet again this would have been a trade-off with increasing the size of the arm, making it more unnatural looking, so I decided to remove it and just put it down to another limitation of this design. So let's go over the way the current version operates. Inside the arm consists of 9 servos. The SG90 servos actuate the side-to-side motion of the fingers, and the 5 larger JX servos operate the inward motion of the fingers and the thumb. The main Kevlar lines that operate the inward motions of the fingers and the thumb are run through the centre of the PTFE tubes. The reason that I've done this is it allowed me to run the Kevlar lines through funny angles without creating too much friction, as the PTFE tubes provide lower friction and equal tolerances throughout their inner diameter. This was a very useful way for me to reduce the overall size of the arm. This allowed me to actuate the lines in a more compact manner without providing a ton of friction to the lines by going around weird angles and in turn putting excessive loads on the servos. The SG90 servos Kevlar line did not run through the PTFE tubes, as I couldn't fit any more PTFE tubes in the palm of the hand, but it worked out okay because this operated over a shorter distance and didn't have to go around any weird angles. All the Kevlar lines go through the arm area, through the wrist and into the palm of the hand. The smaller servos Kevlar lines finish and are connected to each side of the joint that operates the side-to-side motion of the fingers. The lines that are connected to the larger servos continue through the top and bottom parts of the finger and thumb. There are little small pieces of PTFE tube inside the finger and thumb to help them actuate better with less friction. When the servos rotate, they pull on one of the lines and at the same time releasing the tension on the opposite line. This allows the finger to move inwards, actuating the finger. When the servos move back the other way, it opens the finger back out, creating the movement of the human finger. The same action happens with the thumb. This also works the same with the side-to-side motion of the finger by the SG90 servo rotating and actuating each side of the pivot points on the joint. These actuations do produce some pretty lifelike movements, but also come with their limitations. The stepper motor in the elbow joint provides the rotational movement that replicates the rotational movement of the hand and arm. This also worked well, but originally I didn't plan on using such a big stepper motor. Before I used a 32mm NEMA 17 with an 8825 stepper motor driver. The only thing was it had nowhere near the amount of torque needed even to rotate the arm. At first I thought the driver wasn't cut out for the job, so I changed the driver for a bigger CNC stepper motor driver that I had laying around, but the stepper motor was still too small to provide the needed torque that I needed to rotate the arm. I eventually swapped it out for this meaty 60mm NEMA 17 that I had laying around in my parts box. It worked really well, providing all the torque that I needed to turn the arm properly. In future versions I'd like to try out other stepper motors that are smaller that have planetary gearboxes to see if they could provide the torque that's needed, as this stepper motor provides quite a lot of weight to the arm and takes up more space. The hand also has another feature. It has touch sensors in its fingertips so that it can give feedback when it's holding an object or something touches its fingertips. The way that I done this was by utilising a Hall effect sensor and a small 3mm by 0.5mm circular magnet. When the magnet comes close to the Hall effect sensor, the magnetic flux and density around the sensor exceeds a certain preset threshold. The sensor then detects and generates an output voltage. This then gives us the data for the Arduino to read. There is a piece of foam between the magnet and the Hall effect sensor, so when there is no pressure being applied to the fingertip, the foam pushes away the magnet and stops the signal being sent to the Arduino. The Hall effect sensor has 3 wires that need to be connected to it. These wires run through the centre of the finger and through the back plate of the hand, providing the best cable management I could, as it wasn't possible to run the wires anywhere else. The Hall effect sensor also requires a 10k resistor to be connected between the VCC and V output pins of the Hall effect sensor. This is done to pull the output of the Hall effect sensor to 5 volts. Otherwise the sensor would not work with the Arduino. In the next version I would like to use some kind of touch sensor in the palm of the hand as well, and potentially use SMD momentary switches, as they require less wiring and they're small in size. Inside this control box I have an Arduino Mega with a sensor shield with 10 potentiometers that allow me to actuate all the joints. There's also a 5V battery eliminator circuit to help step down the voltage from the LiPo. I'm using a PCA 9685 12-bit PWM servo driver to control all of the servos in the arm. This module was handy as it communicates over I2C. By doing this it only requires 2 pins from the Arduino, freeing up a lot of pins that would otherwise be needed for the PWM inputs of the servos. I've also added some WS2812B programmable LEDs. These LEDs are a bit special as they can be individually addressed with a full range of colour. The way in which they do this is by having a tiny IC inside the LED light. This IC can't be any bigger than the size of a pinhead, and it's amazing how something so tiny works so well. Having this feature has provided the project with a real cyberpunk look. So let's go over all the pros and cons of this version 1, starting with all the cons. There were quite a few issues with this version 1, and the first being that it was just unable to provide all the levels of actuation that the human arm can. As I found out during designing this arm, it was just not possible to get all those levels of actuations with this type of setup, where all the servos are all sort of like in the base of the arm area, you know, especially when you're relying on 3D printed parts. So in the next version, I plan on doing all the actuations on all the joints in the hand area, in the actual hand area. So, you know, this will be more of a challenge, as there's a lot less space in this area to work with. But by doing this, will allow me to create other levels of actuations that were just not possible with this version. Another con with this version was just how hard this thing was to assemble and maintain, and this is just due to the nature of the actuations in the arm. This thing was an absolute nightmare to put together, and it really does take a lot of patience. And you know, it's super fiddly with all the cables running in and out the hand and arm, you know. So in the next version, I hope to make it a lot more modular and you know, make sure it's a lot easier to maintain and, you know, assemble and stuff like that. This is probably easier said than done, but this is going to be the aim of the next version. So moving on with the pros, well, firstly, it's reasonably cheap to build. I think the arm costs around 60 quid in materials, you know, which is pretty cheap for a robotic arm. The components are also really available and pretty easy for anyone to source online. The second pro is that it just uses off-the-shelf components. You know, you don't need to modify them in any way. This makes it a bit easier to assemble, you know, making it more available to more people, and that's pretty much all I've got to say in terms of the pros at the moment. Overall, it's been, you know, a great learning experience, and I've already had some good ideas in the pipeline for the next version. The next version is going to be totally different to this prototype, and I will be prototyping like new ways of getting these actuations to work. So hopefully it will function better than this version, but who knows, it might not. But yeah, you know, I won't know until I try. So I would just like to say thank you for watching this video, and like I said earlier, all the CAD and the code is in the video description. So, you know, if you want to build your own and modify it, it's available. I will warn you though, this is really difficult to put together, and it is definitely a challenge. But if you do succeed, it does work perfectly fine. So please leave a comment in the description if you think there's anything else that I could, you know, could be improved with it. You know, any suggestions would be greatly appreciated. I'm open to everyone's suggestions. Also, if you like the video, it'd be greatly appreciated if you could give the video a thumbs up. And if you want to see more content like this, please consider subscribing. Well, that's it, guys. I'd just like to thank you, and you know, I'll see you in the next video.